We'll now be learning about systems of linear equations, and we'll learn a few different ways to solve these systems. First, we're going to go over a few concepts. So a system of linear equations is given by two or more equations that are linear, so no quadratics, no square roots, no logs or exponentials, and they're going to have two or more variables. So in the simplest case, we're dealing with maybe two equations and two variables. And those two equations are going to generate lines. So you're going to think of, a y equals mx plus b, and then another y equals mx plus b. So we're going to get two lines. And when we graph two lines in the plane, we have three different possibilities. Either the two lines intersect in one point, or the two lines are parallel and never intersect, or the two lines are going to intersect everywhere. Basically, they're two lines happen to be the exact same line, like one right on top of the other. So these are the three classifications of linear systems. A consistent system is where you have one point that's common to both lines. And in this case, we'll have one unique solution. The solution is going to be given by the x and y coordinate of that point of intersection. In this case, we will have what's called an inconsistent system, where there's no points in common to both equations, and in this case we're going to have no solution. In the third case, where the two lines actually represent the same lines, we'll call them consistent and dependent, and in this case we'll have infinitely many solutions to the system. In fact, the solution set is the set of all points on that common line. Okay, so let's go through two methods that you may have seen in the past for solving systems of equations. We've got the substitution method and the elimination method. So let's go through these two methods. We've got our two equations, 2x minus y equals 1 and x plus y equals 5. If we solve by substitution, so by substitution, what we'll do is we'll take one of the equations, say this first one here, and we'll solve for one of the variables. Since it's almost already by itself, let's solve for y. I'll subtract 2x from both sides, yielding negative y equals negative 2x plus 1. Might as well get rid of that negative, so I'll multiply both sides by negative 1. So y equals a positive 2x minus 1. So now that you've got the one equation solved for one of the variables, I'll go ahead and substitute this into the second equation, the x plus y equals 5. So I'll take this y here, which is also represented by 2x minus 1, and I'll replace y with this expression. So this becomes x plus 2x minus 1 equals 5. And now we have a linear equation in just one variable. 3x minus 1 equals 5. Add 1 to both sides and divide both sides by 3. We get x equals 2. And we're not quite done yet, because now we need to plug this back into, say, this equation right here to figure out what y would have to be. Y would be 2 times x, which is 2, minus 1. So y would be 3. So x is 2, y is 3, and we can represent that by the coordinate pair 2, 3. Let's do the same problem, but by elimination. I would say this is a very nice problem for elimination because the coefficient of y, they're exactly opposites of each other. So 2x minus y equals 1 and x plus y equals 5. If you add these two equations together, notice the minus y plus y, those are going to add together to give you 0. So adding down, 2x plus x is 3x, minus y plus y is 0. And 1 plus 5 is 6. Divide both sides by 3. We get x equals 2. So it's a little quicker than this method over here. And then you just have to plug this back into either of these two equations to solve for y. So 2 plus y equals 5. Y will have to be 3. And now we get our solution, 2, 3. So either method works. Things I want us to know that are these two equations, 2x minus y equals 1. Notice, if I solve for y here, we get y equals 2x minus 1. And the other equation, x plus y equals 5, if we solve for y, subtract x from both sides, we get y equals negative x plus 5. I just like to go ahead and graph these two lines. This one I'll graph in this green color. So the y-intercept is negative 1. The slope is 2, so I'll go up 2 over 1 to graph some more points on this line. Connect these points. So there is my first line. The second line, y equals negative x plus 5. I'll graph in red. So 5 is the y-intercept, and the slope is negative 1. So connecting these points. So there are my two lines, and notice that they intersect at this point. X-coordinate is 2, y-coordinate is 3. That's what the solution looks like graphically. So either method here works, by substitution, by elimination, or this third method, which is more graphical and less algebraic. Either one of these leads to the same solution. This next example, let's also solve using both of these methods. We've got negative 2x plus 6y equals 6, and x plus 3 equals 3y. So by substitution, I think I'd rather use the second equation for substituting because x is almost by itself here. So if I start with x plus 3 equals 3y, and I subtract 3 from both sides, I get x equals 3y minus 3. And I'll use this to plug into the first equation, negative 2x plus 6y equals 6. So noticing here, I'll replace x with 3y minus 3. So I've got negative 2 times 3y minus 3 plus 6y equals 6. Continuing here, we get negative 6y plus 6 plus 6y equals 6. And combining my like terms here, negative 6y plus 6y, those add to 0. We just get 6 equals 6. Notice what I have. It is an equation, but it's still a true equation. Now, what is happening here is that no matter what we have for, what we plug in for x or for y, no matter what we plug in for y, we're still going to get a true equation no matter what value you put in here for y. So as long as x is equal to 3y minus 3, we get a true statement. Now, we can say that this will be classified as a dependent. It's consistent, dependent system. What we have here is infinitely many solutions. And the best way to state those infinitely many solutions, here I have a x is 3y minus 3. Typically, though, we'll like write it as by solving for y. So if I instead had solved for y here by dividing both sides by 3, I'd have x plus 3 over 3 equals y. And then I can say that my solution is a set of all points x And then instead of y, you know that y is going to have to be x plus 3 over 3, such that x is a real number. So it's the set of all coordinate pairs like this, where whatever number you plug in for x, add 3, divide by 3, that's the number that you'll plug in for y. And this is how it looks when you try to solve, by substitution, when you try to solve a dependent system. Let's see what it looks like if we used elimination. And I'm just going to write down those two equations. Negative 2x plus 6y equals 6, and x plus 3 equals 3y. But I would like to write it so that the x's and the y's are on the left, and then the number part's on the right. You kind of have to line up all the x's and the y's. So let me subtract 3y from both sides and subtract 3 from both sides to rewrite this system. My negative 2x plus 6y equals 6 stays the same, but now I've got x minus 3y equals negative 3. All right, and I'm going to do one more thing to this system because I don't have any of the coefficients that match up. I'd really like there to be a 2 here so that if I did minus 2x plus 2x, I would get 0. So I'm going to multiply both sides of this equation by 2. That'll give me one more time. I've got negative 2x plus 6y equals 6, and positive 2x minus 6y equals negative 6. And then when I add those two equations together, minus 2x plus 2x is 0, plus 6y minus 6y is 0, and then 6 minus 6 is 0. So what we get, again, is a dependent system. Again, what happens is that if you go through the whole process of solving, you end up with a true equation, then you've got infinitely many solutions. Let's do one last example. 2x minus 3y equals 3, and 3x minus 9/2 y equals 5. Let's solve by substitution. I'll take that first equation, 2x minus 3y equals 3. And why don't I go ahead and solve for y? I'll subtract 2x from both sides and divide both sides by negative 3. I'll get 2/3 x plus 3 over negative 3 is minus 1. And now let's go ahead and plop that into my second equation. 3x minus 9/2 y equals 5. That's 3x minus 9/2 times 2/3 x minus 1 equals 5. Let's go ahead and open up these parentheses. Negative 9/2 times 2/3, so the 2's cancel. The 3 goes into 9 3 times, so we get minus 3x. And then negative 9/2 times negative 1, we'll have plus 9/2 equals 5. The 3x minus 3x, that adds to 0, and what we end up with is this completely preposterous equation, 9/2 equals 5. This is an inconsistent system. Therefore, we have no solution. So this is what these look like. If you were to graph these two lines, you'd see that they are two parallel lines that never intersect. If you graph these two lines, you'll see two lines that actually happen to be the same line. They intersect everywhere.